Hello, students. Today, we're going to dive into a very important topic in electrochemistry, the electrochemical cell. You must have seen this, no? It looks like some kind of magic trick, but it is pure science. And the secret behind this simple but amazing phenomenon is exactly what we are going to understand today. And this is why this topic is so important. You see, from the small cell in your remote control to the large battery in your phone, the basic principle is exactly the same. So if you can understand this concept, you will understand the heart of how all modern portable power works. Okay, so let's get into it. The name electrochemical cell might sound a bit complex, but I promise you, the main idea behind it is actually very, very simple. That is it. Really, at the simplest level, all we are doing here is creating a special setup, a controlled system where a chemical reaction happens on its own, and this reaction causes electrons to move from one place to another. So just picture this in your mind. You have two different metals. Now, because of their basic chemical nature, one metal has a stronger tendency to lose its electrons. We call this process oxidation, while the other metal has a tendency to gain electrons, and we call that reduction. It's like they have a natural preference. So how do we make use of this? Well, it's simple. We just give the electrons a pathway to follow their natural tendency, and that path is a wire. This controlled flow of electrons, moving from one metal to the other through the wire, is what we call an electric current. And just like that, we have generated electricity. Okay, now for your exams, here is the formal definition you should remember. An electrochemical cell is a device where a redox reaction, that's the combination of oxidation and reduction we just spoke about, takes place. Now, in this process, electrical energy can either be produced, like in a battery, which we call a galvanic cell, or it can be consumed to force a reaction to happen, which is an electrolytic cell. For today, we are focusing on the first type, the ones that create power for us. Now, please pay close attention. This is a very common point of confusion that I want to clear up right now. Students often mix up the flow of electrons and the flow of ions. So please remember, the electrons, which are the stars of the show, they travel through the external metal wire. But for the circuit to be complete, charged ions must flow through the internal liquid solution, which we call the electrolyte. Both flows are absolutely necessary. Now, to make this idea really stick in your mind forever, let's use a simple analogy from nature. Think of an electrochemical cell as being just like a waterfall. Water naturally flows from a high point down to a low point, correct? Well, in our cell, the electrons are just like that water. They flow from a high energy point, which we call the anode, where oxidation happens, down to a low energy point, the cathode, where reduction happens. The flowing water is like the flowing electrons in the wire. And just like an underground channel might complete a water cycle, our electrolyte solution allows ions to flow and complete the electrical circuit. It's a natural, spontaneous, downhill flow of energy. And this simple idea was absolutely revolutionary. Before this, you see, electricity was just a spark from static or a sudden flash of lightning. But Volta's discovery in 1800 showed the world how to take the chemical energy stored inside substances and convert it into a steady, controllable, and portable flow of electrical energy. This discovery completely changed everything. All right, now let's build a very clear mental picture of a standard electrochemical cell, the kind you would see in your textbook or in the lab. We will build it together step by step. Let's start with the basics. Imagine two glass beakers sitting on a table. These will hold our two separate half reactions, and we'll also need a salt bridge to connect them internally, which is very important to complete the circuit. Now, let's add the main components. In the beaker on the left, we place a strip of zinc metal. This is our zinc electrode. In the beaker on the right, we place a strip of copper metal, our copper electrode, and each metal strip is sitting in a solution that contains its own ions. The next step is the most important one. We need to provide a path for the electrons to travel. So we take a simple metal wire and connect the top of the zinc electrode to the top of the copper electrode. The moment you make that connection, the reaction starts. You see, zinc has a stronger tendency to lose electrons. So atoms on the zinc electrode start giving up their electrons. They become zinc ions and dissolve into the solution. These electrons that have been freed then rush through the wire, moving towards the copper. This is oxidation. So what happens when these electrons reach the other side? Well, in the copper beaker, there are copper ions floating around in the solution. They are waiting, and they eagerly grab these incoming electrons from the wire. When they do, they turn back into solid copper atoms and deposit onto the copper electrode. This is reduction. And this entire coordinated process generates a steady electric current. All the while, the salt bridge is allowing ions to move between the beakers, which maintains electrical neutrality and keeps the current flowing smoothly. So I am sure you are thinking, okay, this setup with beakers and wires is fine for a laboratory, but where do I actually see this in my real life? Well, the truth is, you see it and use it every single day. Let's just take a common AA battery, the kind you put in a flashlight or a remote. The outer casing of that battery, that's usually made of zinc, and that is your anode, the source of electrons. Inside, in the center, there is a carbon rod, that is your cathode. And packed in between them is a moist chemical paste that acts as the electrolyte, allowing the ions to flow. So when you put the battery into the flashlight and switch it on, you are simply connecting the external wire, which completes the circuit. This allows that natural flow of electrons to happen, and that flow powers the bulb. All right, we have covered a good amount of ground. So before we finish, let's just quickly recap the 3 most important things you need to take away from this explainer. First, always remember the core idea. We are simply capturing the energy from a natural flow of electrons, from a substance that wants to lose them to one that wants to gain them. Second, hold on to that mental image, the waterfall. Electrons are always flowing downhill from the high-energy anode to the low-energy cathode. And third, the real example. Just think of any simple battery. It's nothing but a compact, neatly packaged electrochemical cell. I can promise you, if you can clearly remember these 3 things, the simple core idea, the waterfall picture, and the flashlight battery example, this entire topic will become much, much lighter for you to handle, especially when you are sitting in your exam. And I'll leave you with a question to think about. We've discussed how a battery produces electricity, but when you plug your phone in to recharge it, what do you think is happening inside the battery then? This time, we are putting electricity in. Think about it. We will explore that very question in our next explainer. Thank you.